Now, what if you were asked to solve these DC circuits? What if you were asked to find out the currents and the potentials at the various positions that are represented here, and also to find the voltages that will be wasted over each resistor? If you were asked these questions, how would you solve it? Now, the very best method you would need to do that will be by the method of Kirchoff's laws, the current law and the voltage law. So we're actually going to solve them one after the other. Let's start with the first DC circuit. So here we have 28. That will be 28 volts. And over here we have 2 ohms. Here we got 4. This will be 3. Here is 3 as well. And here we got 5. We have 2 volts here. So this is 2 ohms. This is 4. This is 3. This is 3 as well. And this is 5. And the next thing you need to do is to assign letters to each point within the DC circuit. So we're going to say this is point A. Let's say this is B. Let's say this is C. And this will be D. Let's say this is E. We're going to call this F. Next up, you need to find out the terminals for each element within this DC circuit. So let's start with the battery. Now the battery has a positive terminal and a negative terminal. In this case, we have the longest stroke that's visibly represented there, and the shortest stroke that will be the negative terminal. So let's say this is the positive, this will be the negative. Now you need to understand something real quick. If you have the positive terminal of the battery represented, you need to understand that that will be the direction in which the current will flow. So current is actually going to flow in this direction. Now let's say that the current that enters into the circuit from this battery, let's say that is I1. So let's call this I1. Now let us introduce the concept. If you have current moving in a direction, let's say this is a wire, and you have a resistor connected across it. Let's say this is point A, and this is point B. Now, if you have current moving in this direction, what that means is there is going to be a potential at point A that is greater than the potential at point B. So that's really just the reason you're going to have current push toward this direction. So the higher potential at point A really just pushes the current to point B. And if you have it that way, then you can tell the terminals or the symbols of the terminals for the elements or the resistor. So since we have this part or this side of the resistor being at a higher potential, I could say this is positive, and we know that it goes towards the potential or towards the point where the potential will be lowest, so that will be a minus. And that's basically how to apportion those symbols for each element, that is each resistor. Now there is also another thing you need to understand. Let's say that you have a resistor like this. This is point A, and this is point B. When solving these questions using the method of KVL, that is the Kirchoff's current law and the voltage law, you would actually be required to move in various directions. So let's say, for instance, you have already designated the terminals for a battery, and you're actually moving in this direction. That is the motion that you would use to analyze each loop. This DC circuit you see here, this contains 2 loops. This is going to be the first one. This is the first loop, and this will be the second. So for each loop, you would need to go in a particular direction to find out what will be the voltages or the currents that will be responsible for various physical quantities that will be formed basically. So if you move in any loop in a direction, you should be able to tell what will be the effect of the voltage or the potential. So let's say, for instance, you moved in this direction, represented here. Now you can see that this arrow points towards the negative terminal, or the negative charge. So that is going to cause a voltage drop. So the potential will be reduced as you come to this point. If, however, we had it this way, so let's say this is plus and negative, and you had the motion through the loop going in that direction, that means this is going to be a voltage rise. That's because the arrow ends on a positive note, or that indicates that it ends on the negative charge. So there will be an increase in voltage on that note. So you need to hold this at the back because we're going to use these principles to work to find the answer within this question. So let's come back here. Now we know obviously that the current is moving in this direction. So obviously this part will be higher and this will be the lower potential. Now as the current comes to point B, there is going to be a split. That is because B is a junction. And at a junction where you have current approach the junction, you should have a split. So let's say some currents goes downward and another goes upward, or in that direction. So let's say the current that goes here, let's call that I2. And let's call this I3. That is the current that goes through to the point C and down. So this will be I3. Now let's talk about I2. As I2 comes downwards from point B to point C, you can see that the direction of the current is toward point C. That means B has a higher potential as compared to E. So this will be a positive terminal, this will be a negative. Now considering I3, we have I3 pass from the point B to the point C. And so we're going to say that this has a higher potential as compared to the other side, where you approach C. Now, because we have this as a casual bend, or just a normal bend, you're going to have the I3 go downwards. So I3 will go to D. Unfortunately, here we just have a battery, so you don't really need to consider whether or not there is going to be a negative or a positive, because that is visibly represented. You can see that the longest stroke for this battery is in this direction, so you just need to write the positive there. There's actually nothing you can do. Then here you're going to have a negative. Now we know that that current goes downwards and bends in its direction and goes this way, right? So as it goes this way, we know that this is going to carry a higher potential and this will be the negative. So you need to understand that as I1 comes down, that reinforces with I3 to reform I1. Remember, I1 is equal to I2 plus I3. Right? So that's what you have. So if you have I2 plus I3 combined, that would reform I1. So I1 will be the current that goes through 5 ohms. And we know that pushes in this direction. So the point E would have a higher potential as compared to the point F. So this will be positive and this will be negative. Now the last thing you need to do is to label each resistor. So let's say this resistor is R1. Let's call this R1. Let's say this one is R2. That is this resistor. Let's say that is R2. Let's say this one is R3. Well, I think I'm going to change that. Let's make that one R2. So let's say this is R2. And let's call this R3. Now this is going to be R4. Let's say this is R4. And let's say this is R5. So that's basically it. Now this equation you see here, this is actually an equation as a result of Kirchoff's current law. Kirchoff's current law states that if you have current coming towards a junction, it splits up into more than one current, maybe 2 or more, such that the sum of the currents that enter the junction will be equal to the sum of the currents that leave the junction. So because of that principle, you'll have this equation. And we're really going to use it later on. For instance, from here, you can say that I3 is equal to I1 minus I2. So this is really just another way to find some stuff. Just bear that at the back. So now we're going to solve this circuit starting with the first loop. So let's say this is the first loop, loop 1. And we're going to use KVL, the Kirchoff's voltage law, for the first loop. Now what does the Kirchoff's voltage law say? It says that the total voltages or potentials that will be wasted within a loop would be equal to 0. So within a closed loop, if you add all the potentials that will be wasted, that must be equal to 0. Now let's use that principle to solve this. Now for the first loop, we're actually going to choose the direction with which we'll perform the analysis. So I would actually prefer to go in this direction. That is the clockwise direction. So what that means is I need to analyze each element you see within this first loop. We got this, this, and this. So we just got 4 elements within the first loop. Now the first element will be the battery. As a matter of fact, that is the reason I chose the clockwise direction, because current goes in this direction with respect to the battery. But you could actually choose to go another direction, and that pretty well is still going to be correct, but most times you just want to go in conventional methods, so I'll just be restricted with that. Now for the first element, the battery, if we run in this direction, you would find that we're actually going to end on a positive note for that element. And so that will be represented as plus 28 volts. Now remember, we're basically just dealing with the voltages that will be wasted on each element. From Ohm's law, voltage is equal to I multiplied by R. That is the current multiplied by the resistance. So over here, of course, we do not really know the visible value for the voltage wasted over that resistor. But we know that if we take I1 and multiply by R1, we're going to find the voltage that was wasted over 2 ohms. But we know there is going to be a voltage drop because we're moving in this direction. So if you move in that direction, that is going to be a voltage drop. Now we do not really know the voltage, but we know that if you take I1 and multiply that with R1, that will give you the voltage. Now the same thing goes for the second resistor, the 3 ohms resistor. Now of course the current goes downwards, so that ends on a negative note. So that will be minus I2 multiplied by R2. Now the last element within this loop is the 5 ohms resistor. And we know that I1 is a total current that goes through the 5 ohms, and that ends on a negative note. So that is going to be I1 multiplied by R5. And all these got to be equal to 0 according to the Kirchoff's voltage law. Feel free to rewind the video, just go back there where we talked about that. So right now we're going to have 28 volts minus I1 multiplied by R1. Now R1 in this case is 2 ohms, so I just got to write that there. Okay. Now R2, that is our 3 ohms. Now R5, that is our 5 ohms. So right now we're going to have 2 I1 with 5 I1. That will be minus 2 I1 minus 5 I1. That gives us 7 I1. So this is 28 minus 7 I1 minus 3 I2. Okay, this is equal to 0. So I'm just going to take these ones to the other side. That will be 28 is equal to 7 I1 plus 3 I2. Now you could actually rewrite it this way. So this will be 7 I1 plus 3 I2, and that will be equal to 28. So this is the first equation. So what that means is the first loop creates a first equation, and the second loop is going to create another. So you're just going to use the method of simultaneous equations to find out the value of all the unknowns. So right now we're going to the second loop. So this is the second loop, number 2. Now within the second loop, we got 4 elements. Notice that 3 ohms, that was a resistor that was part of the first loop, but that's still going to serve as a part of the second loop. Within the second loop, we got 4 ohms, the 3 ohms battery, another 3 ohms battery, and a 2 volts. Whoa, these are resistors. That was a gross mistake on my part. So there's got to be 2 volts. That is a 2 volts battery. So let's start with this one. Now the direction for the analysis will be this way. That's because we have already started with this, and basically this battery, it's really just a small battery, doesn't really have so much EMF, so that would not cause the current to go this way. Now we're going to start with the first element, which is the 3 ohms, and that ends on a positive note, so that will be plus, but we do not really know the voltage wasted over the 3 ohms, but we know that that will be equal to I2 multiplied by R2. Next up, we got the 4 ohms. So that ends on a negative note, which you see there. So that will be I3 multiplied by R3. Next up, we got this stuff. Now remember, we're moving in this direction, so that will go down, and we're going to end on a negative note, so that should be a voltage drop. But we know the voltage already. That is 2 volts, so we're just going to write it there. Now the last one is this. That will be negative I3 multiplied by R4. That's equal to 0. Now remember, we said that I3, that should be equal to I1 minus I2. So we're actually going to use it later on. Let's find out what the values of the resistors are. Okay, so this is going to be I2 multiplied by R2. Now R2 in this case is 3. And R3 that is 4 minus 2 volts. Now R4 that is a 3. This is equal to 0. Now we could take negative 4 I3 and subtract negative, I'll subtract 3 I3 from it. Basically, that is the addition of these two in the negative. That will give us a negative 7 I3. So here now we have 3 I2 minus 7 I3. And I'm just going to take this 2 to the other side. So that will be equal to 2. Now remember, we said I3 is equal to I1 minus I2. So I'm going to plug that back in. So this is going to be I1 minus I2. Okay, and that's equal to 2. So let me take negative 7 and I'll open the bracket with it. So this will be minus 7I1. Here I'm going to have plus 7I2. And this will be equal to 2. Now from here we have 3I2 plus 7I2. That's going to give us 10I2. Well, we have negative 7I1 here. So I'm really just going to write it first. Plus 10I2. This is equal to 2. So that really is going to be the second equation. This is minus 7I1 plus 10I2. This is equal to 2. So these are the two equations we have. Now we're going to solve them simultaneously and find out what will be the value for I1 and I2. And because of time, I'm just going to use my calculator to do that. So what we have for the coefficient of I1 in the first equation is 7. Then we have plus 3. And then we have 28. And for the second equation, we have minus 7. And we got 10. And we have 2. So I1 that's equal to 3.01. So let's just say 3.011 amps. and I2 is equal to 2.308. amps. Now from here we can find out what will be I3. We know that I3 was supposed to be I1 minus I2. So let's find that out. So if you have 3.011 minus 2.308, that gives us 0.703. So I3 here, that is 0.703. So this will be the third current. So now you can say you've found all the currents that will go through each resistor within this circuit. Now we're not actually done just yet. We still need to find out the voltages that will be wasted over each resistor. We'd also need to find the potentials at the various positions. So let's briefly talk about that. Now at the point A, we're actually going to have the EMF of the battery situated there. That is because between the battery and point A, we don't really got no element or no resistor. So that's just going to be 28. So the voltage at point A, that will be equal to 28. So that's 28 volts. Now what's going to be the voltage or the potential at point B? Now as the current moves from point A to point B, it's going to come across the resistor 2 ohms, and that would reduce up the voltage. That's the reason you say there is a voltage drop at that point. So what's the voltage wasted over that resistor? We could call that V1. Now sometimes you could actually be asked to find out the voltage wasted over such resistors. If you are required to do that, basically that will be I1 multiplied by R1 from the Ohm's law. Now I1 we have actually found out to be 3.011. That will be multiplied by R1. So this should be 6.022 volts. This is the amount of voltage that will be wasted over the first resistor. Now you could use this formula to find out the voltages wasted over all the resistors. So you could find V2, V3, V4, and V5. So in order to find the voltage or the potential at point B, we have to take the voltage or the potential at point A and subtract the voltage wasted over the first resistor. So we know that is going to be 28 minus 6.022. That gives us 21.978. Well, this is 21.978 volts. Now let's find out what will be the potential at point C. Now because we have the current I3 going through to that point, VC, the potential at point C, that should be VB minus the voltage wasted over the third resistor. This is the third resistor. Now we know this is going to be VB minus V3, which is going to be I3 multiplied by R3. So VB, that is 21.978 minus I3 that is 0.703 multiplied by R3. R3 is 4. So that's going to be 19.166. That will be the voltage left at point C. Now feel free to find out what will be the voltage wasted over the third resistor. I actually included that in the solving for VC, the potential at point C. The voltage wasted over the third resistor will be V3, and that will be equal to I3 multiplied by R3. So feel free to find that out. Next up, we got to find the voltage wasted, or let's say the voltage left at point D. Now VD, that is going to be VC minus the voltage wasted over that entity, which is a battery in this case, and that's basically 2 volts. So this will be 19.166 minus 2, that will be 17. So VD should be equal to 17.166 volts. And the next one is VE, the potential at point E. VE will be equal to VD minus the voltage wasted over the 4th resistor. So that could be written as V4. So we know VD, that is a 17.166. That will be minus V4. V4 is I3 multiplied by R4. Now I3 is 0.703 rather. That will be multiplied by R4, which is 3 in this case. And so that's equal to 15.057. So VE is equal to 15.057. Am I correct with that? Yeah. Now let's go on to VF. The voltage wasted over the 5th resistor. You need to take that voltage away from the potential at point E. That will give you the potential at point F. So that's a basic V sub E minus V5. Now V sub E, that is 15.057. So that will be minus V5, which is that should be. So you got to understand this. V5 is going to be equal to I1 multiplied by R5. Because we had the second current and the third current. They actually rejoined at point E and went through the 5 ohms resistor. So I need to take that. I1, that is 3.011. And that will be multiplied by 5. So here now, VF is approximately 0. What you got is this. That is 0.002 volts, which is approximately equal to 0. And wherever you have the point to give you a 0 volts, that is a place where you're going to call the earth. That's what is called the ground. So I could well change this and represent it here. This is the ground. So VF, or the point F, that is where you're going to place the ground. That means there is no voltage at that point. And so that's basically how to solve it. Now let us go on to the second DC circuit. That one contains 3 loops. That should pretty well still be simple because we're really just going to use the Kirchoff laws again. I think I'm going to take these out. Okay. So the second one is, I need to retake that again. Okay. So this is a battery. Here we have another resistor. This is another resistor. This is another. And here we got another battery. And here this is a resistor. So yeah, this is what you have. So right now this is 96 volts. And this is 1 ohms. This is 4 ohms. Here you got 2. Here this is okay, that is 1 as well. And over here you got 2. Here this is 3 volts. And that is going to be 4. And here you're going to have 3. And from the last part, we got 4 volts. I'll show that. So let's represent these positions as A. Let this be B. Here we're gonna have a C. So this is a D. That is an F. Here you got an F. We're gonna have a G there. That will be an H. So the terminals here, we're gonna have a positive. This is gonna be a negative. So the current obviously is gonna go this way. So this is gonna be I1. That is I1. Now let's say this is R1, the first resistor. Let's call this R2, second resistor. Let's say this is R3. Let's call this R4. I'm gonna write the R4 here. Let's say this is R5. And here we got R6. And this will be R7. So now let's talk about the currents. We got I1 emanating from the battery 96 volts. So as I1 comes from A to point B, at point B there's going to be a split. So let's say that I1 splits into I2, and in this case we're just going to use something different. Let's say this is going to be equal to I1 minus I2, which is really actually the same thing, because we don't want to create more variables here. The problem is the more variables you create, the more simultaneous equations you would actually need to solve. And you don't really want to have too many simultaneous equations. That would actually take more time. So in this case, we're just going to say it, because we know that if I2 comes through the second resistor, the rest of the current is actually what is going to go through the rest of the circuit. So we're going to say this is I2. This is I2. And the current now goes through this whole part. That current will be called I1 minus I2, because it's actually going to be gotten if you took I2 away from I1. So I'm going to represent that here. Current now goes through this. Let's call that current I1 minus I2. Now we know that I2 comes to the point C. Now as it comes to the point C, there's going to be another split. So let's say the new current that goes through the 4 ohms resistor, let's say that current is I3. I3 will be a current coming out of I1 minus I2 that goes through the 4 ohms resistor. So let's call this I3. Now what is going to be the rest of the current that goes through the remaining part of the DC circuit? That would obviously be I1 minus I2 minus I3. Because if you take I3 away from this current, you're going to have the remainder, which of course should go through the last part of the DC circuit. So this is what we're going to have. I1 minus I2 minus I3. This is a typically simpler version of doing this. This actually saves a lot of time. So let's deal with this. Now the next thing we need to do right now is to find out what would be the terminals for each element. So for the first resistor, we know the direction of the current. So this is going to be the positive terminal, that will be the negative. Now over here we know the current goes downwards, so this will be positive and that will be negative. Now you need to understand something. If you have I1 going through the first parallel section of the DC circuit, that will pretty much well be the same current that goes through the other half parallel of the DC circuit. In this case, we know that this section is really just parallel to this section. So if you have I1 going through that first parallel section, that will be the same current that goes through the second half. Therefore, I1 is going to go through this. So bear that at the back. Now over here, we have I1 minus I2 go through this parallel section. So the current that will go through the second parallel half will be I1 minus I2 as well. The current that goes through the 2 ohms resistor, that will be I1 minus I2 minus I3. That's going to be the same current that goes through the 1 ohm resistor. So bear that at the back. Now we know that the current moves in this direction. So as we move in this direction, we're going to have the positive terminal situated here, and the negative will be here. Now for this battery, this is going to be the positive terminal, this is going to be the negative. Here, this is going to be the positive, and this will be the negative. Now let us talk about this resistor. We know that I3 goes downwards. So this should be positive, this should be negative. Now over here, we know the current moves in this direction. So that would cause this to carry a positive charge, and that would be a negative as it goes toward this side, because the higher potential pushes it. Now here, we're also going to have positive and negative because currents will go through that direction. You got to understand that I3 is going to remerge with I1 minus I2 minus I3. That would yield I1 minus I2 as it goes through this section. And finally, this is going to be positive and this will be negative. So that's pretty much it. Now let's find out the KVL equations for each loop. Let's start with the first loop. This is the first loop. Now because we have the direction of the current going that way, we're still going to use that direction. So this is a clockwise direction. And this is the first loop. So the first element here is 96 volts. That is the EMF source, and that is 96 volts. And that ends on a positive note. So that will be 96. Over here, we know that this is I1, and that would end on a negative note. So that will be I1 multiplied by R1. The next one is the R2 resistor. And I2 is the current that goes through it. That ends on a negative note. So that will be minus I2 multiplied by R2. The last one is the 4 ohms resistor. Now, as I told you, you have I1 going through the first parallel section above over here. So that pretty much is going to be the same current that goes through the next parallel half, which is the 4 ohms resistor. And we know that ends on a negative note with respect to the charge. So that will be minus I1 multiplied by R7. And this all is equal to 0 according to the Kirchoff voltage law. So this is going to be 96 volts. Now R1 is 1. And R2, that is 3. R7, that is 4. Now here we're going to have negative I1 minus 4I1. That gives us negative 5. So this is 96 minus 5I1 minus 3I2. Okay, so this is equal to 0. Now I'm just really going to take these to the other side. So that will be 96. And this is going to be equal to 5I1 minus 3I2. So I'm going to write it out somewhere over here. Let's remember that. That is 96 is equal to 5I1. 96 is equal to, okay, I think I'm going to write it this way. So we have 5I1 minus 3I2. And this equal to 96. So let's say this is our first equation. Now the first loop really comes off pretty easy. Let's see what's going to be given for the second. Right? So here is the second loop. This is going to be number 2. This is how it goes. Hopefully you understand that. We're really just using the clockwise direction for each of them. Okay? So let's see what we're going to see. So right now we're going to start with this. Now for this part, you can see that this ends on a positive note if we were moving in this direction. And that's actually the direction we're going in. So that will be a plus. Now we know that the voltage wasted over the 3 ohms resistor that will basically be I2 multiplied by R3. And next up we have this battery. That's a basic 3 volts. But that would end on a negative note as we go in that direction. So that is going to be minus 3 volts. Now for this part, we have 4 ohms, that is R3. And the current that goes through that resistor is I3. And of course this ends on a negative note. So that will be minus I3 R3. And the last one is this. Now what is going to be the current that goes through the 6th resistor? So that is the 2 ohms resistor. Is it going to be R3, that is I3, or is it going to be I2? Which one is it going to be? Now like I told you, the parallel first half of this section is this one. And the current that goes through that section is the I1 minus I2. So that is going to be the same current that goes through the 2 ohms resistor. So you really just got to hold that at the back. So 2 ohms, that is going to receive a current of I1 minus I2. And that ends on a negative note. So that will be minus, okay, I'm going to represent this in brackets. Well, so that is I1 minus I2. That will be multiplied by R6. So that's it. We just got 4 elements within the second loop. So all these gotta be equal to 0. Now what is R2? R2 is 3 ohms. That is the second resistor. So this is I2 multiplied by 3 minus 3. And here we're gonna have minus I3 multiplied by R3. R3 in this case is 4. Gotta represent that there. Next up we got this. That is I1 minus I2. Now R6, that is 2. This is equal to 0. So here now we're gonna have 3 I2 minus 4 I3. And we're gonna have negative 2 I1 plus 2 I2. This will be equal to 0. So we have 3 I2 here plus 2 I2. So that gives us 5 I2. So right now we're gonna say that we have minus 2 I1 minus 4 I3 plus 5 I. Whoa, I'm gonna write out the I2 first, or just before I3. So that will be 5 I2, and here we're gonna have a negative 4 I3. This will be equal to 3. Remember, there was actually a 3 that was a negative, this one here. So if we take it to the other side, we're gonna have a positive 3. So this is an error I need to correct. So that's what you're gonna have. So that will be equation 2. You got negative 2 I1 plus 5 I2 minus 4 I3. Okay, that is plus 5 I2 minus 4 I3. This is equal to 3. Now let's find out what is going to be the equation for the third loop. So this is a third loop. And of course, we're still going to move in this direction. Now, of course, here we also have 4 elements. The first one is this. Now the current that goes through 4 ohms is that's I3. So that will be a positive because we're actually going upwards. So that ends on a positive note for that. That will be plus, I'm going to rewrite that, plus I3, R3. Next up we have this. Now the current that goes through the 2 ohms resistor situated there, that is R4. That current is going to be I1 minus I2 minus I3. So that is going to end on a negative note. So this is going to have something like this. That will be I1 minus I2 minus I3. This is multiplied by R4. And the next one is a typical battery, which ends on a negative note. So that's a -4. And the last one is 1 ohms. Now we know that is going to be the same current that goes through 1 ohms. So that will be minus. Here now we got I1 minus I2 minus I3 multiplied by R5. This is equal to 0. Now R3 is that is 4. So that will be I3 multiplied by 4. We're going to have I1 minus I2 minus I3 here. Now R4, what is that going to be? That's 2 ohms minus 4 volts. Here we're going to have I1 minus I2 minus I3. That will be multiplied by typical 1. This is equal to 0. Here now we have -2 multiplied by this bracket minus 1 multiplied by that bracket. So that should give us -3 multiplied by the bracket. So this will be 4. That is 4I3. Here we're going to have -3 multiplied by the bracket I1 minus I2 minus I3. That bracket will be closed. And this -4 volts, I'm just going to take it up to the other side. So I need to take -3 and FOIL the bracket. So that will be 4I3 minus 3I1 plus 3I2 plus 3I3. This is all equal to 4. Now here we have 4I3 plus 3I3. That gives us a 7. So the real equation is -3I1 plus 3I2, okay, plus 7I3. This is equal to 4. So I'm going to take it to this other side. Minus 3I1 plus 3I2. That will be plus 7I3. This is equal to, that is -4, right? Here we take this. So that's 7I3. This will be equal to negative, well, that's a +4. So are we on track with this? Let's find out. Yeah. So we're actually correct. And this will be the third equation. So this is a set of simultaneous equations we have. And I'm really just going to use my calculator to solve it because we don't got time. Need to redo that. Okay. So the first one, we have 5 as a coefficient for I1. And we got -3 as a coefficient for I2. We don't got no I3 for equation 1, so that's really just going to be a 0. Now we got 96 on the other side. Now for the second, we got -2. There is a +5 and -4. And on the other side, we got a 3. And the next one, we got a -3 plus 3 plus 7. That is equal to a 4. So I1, which is the first current, I think I'm just going to write it here. We got 29.446. Let me take it down. So this is what we have. Next one, that is I2. That is our 17.076 amps. And the last one, that is I3. That will be equal to 5.873 amps. Now we're going to try to make some things work. So let's find out what I1 minus I2 is. So I1, that is 29.446. And I2, that is 17.0. That is 0.076. So that's equal to 12.37. This is what we have. That is amps. Now we got to find out what will be I1 minus I2 minus I3. So this stuff which you have here, 12.37. I would subtract I3 from that. So that is minus 5.873. That gives us 6.49. So this is what you're going to have. So now you have actually found the currents. The next thing you need to do is to find out the voltages present on the various positions represented, or just find out the voltages. Well, let's just find out everything, right? So I think I'm going to take some stuff out of here. Let's take these away. So I1, that's equal to 29.446. I2, that is our 17.076. Now I3, that is 5.873 rather. 5.87. Now what is I1 minus I2? So we already got those ones here. Well, I'm just going to shift it. This is a 12.37. Now I1 minus I2 minus I3, that is 6.497 amps. So we know that the potential at point A, that's going to be the potential or the EMF of the battery. So V sub A, that will be equal to 96. Now V sub B, that is going to be VA minus the voltage wasted over the first resistor. That's V1. So that will be 1 multiplied by 29 point that. So basically that should be 96 minus 29.446. So that gives us 66.554. Now the next one is VC. So what is going to be VC? VC will be equal to VB minus the voltage that will be wasted over the 3 volts battery. So that's basically a minus of 3. Now 66.554 minus 3, that will give us 63.554 amps. Whoa, these are voltages. I gotta write volts there. Now how about VD? So we know that VD should be equal to VC minus V4. That is the voltage wasted over the 2 ohms resistor. Now V4, that has to be 1 minus or I1 minus I2 minus I3 multiplied by R4. That is the current going through the 4th resistor. You got to multiply that with the resistance itself. That gives you the voltage wasted over the 2 ohms resistor. Now I1 minus I2 minus I3, that's equal to this, 6.497. So we got to multiply that with 2. 6.497 multiplied by 2. That gives us 12. So you have to subtract VC. Or you have to subtract 12.994 from VC. So that will be 63.554. And as that will give us 50.56. So VD, that's equal to 50.56 volts. Now how about VE? So VE, we're basically just gonna subtract 4 volts from VD. So that is a minus 4. So if we subtract 4 from this, that is going to give us 46. So we're going to have 46.56 volts. Now what will be VF? VF, that will be VE minus the voltage wasted over the 5th resistor. So that is V5. Now what is V5? V5 is equal to this current, because that is going to be the current that goes through that resistor, right? And so if it goes through it, we're going to have that multiplied by the resistance itself, which in this case is just the basic 1. So if you multiply 6.497 by 1, that gives you pretty much the same thing. So that will be VE minus 6.497. VE, that is 46.56 minus 6.497. So that gives us 40.063. Next up, we got to find out the potential at point G. So that's our V sub G. Now V sub G should be VF. Now that is because we're obviously moving in that direction. So if you're actually moving in that direction, then you need to have the potential at the previous location to be higher than the potential at the destined location where you're actually headed for. So V sub F, if you subtract that, or subtract the voltage wasted over the 6th resistor from this potential, you're going to find out what will be the potential that will be left over at point G. Now V6, remember I told you that this is actually a parallel half of the parallel half above. And so because we have I1 minus I2 going through that parallel half, that is pretty much going to be the same thing that goes through the 6th resistor. Now I1 minus I2 is represented here, 12.37 amps. So we're going to take that and multiply it with the 6th resistor. So that will be 12.37. That should be multiplied by 2. If you multiply that by 2, that's going to give you 24.74. So that is going to be the voltage wasted over the 6 resistor. So here now what we're going to have is VF. That will be multiplied, rather subtracted with 24.74. So that is going to be VF, which is 40.063 minus 24.74. So in this case, you're going to have 15.323. 15.323. So this is going to be 15.323 volts. Now, what about the last one? What is going to be the potential at point H? So that has to be Vg minus V7. That is the voltage wasted over the 7th resistor. You should subtract that from Vg. So this is going to be 15.323 minus 4 multiplied by I1. Now I1, that is 29 point, wait, need to rewrite that, 0.446. Now notice that this is going to be grossly incorrect. Let's find out. That will be 15.323 minus 4 multiplied by 29, 0.446. That gives us negative. So that will be a negative 102.461 volts. So that will be the potential at point H. Now, if you have a negative, what that means is there is a deficit. You gotta have an extra 102.461 volts to be able to sustain the circuit. In this case, we do not really have that. But this is going to be the potential at point H. And so that's basically how to solve it. That is how to work through these DC circuits using the KVL and the KCL.